Alright, in this video we study a class of series that are called power series that contains powers of a variable. Okay, here's the definition of a power series. Power series. First, let an be a sequence of real numbers. And b be a real number, and x be a variable. So here's the definition of a power series. That is a series of powers of x minus b to the power of n. So that is a 0 plus a 1, x minus b, and a 2, x minus b squared, and so on. So this is a power series. Centered at x equal to b. But if we set if we define a new variable t that is equal to x minus b, then we have a power series centered at t equal to 0. So this will be something like this: an t to the power of n. So this is a power series in terms of variable t centered at t equal to 0. So in most cases, we only deal with this type of power series centered at 0. And let's see an example. Consider a polynomial that is a 0 plus a 1x plus a 2x squared and so on up to a n times x to the power of n. So this is a polynomial function of x, but this can be regarded as a power series if we set an plus 1 and an plus 2 and so on are equal to 0. So this is a polynomial is a special case of a power series. More generally, if we have a power series such as this one, ak times x to the power of k, and k varies from 0 to infinity, and all these coefficients ak's are 0 except for a finitely many k's, then this power series is actually a polynomial. If a power series is a polynomial such as this one, then this is a function of x. So we can substitute x with any real numbers. So x equal to 1, we get some value, and when x is equal to -1, we get some value, and so on. But when infinitely many coefficients, ak's, are not 0, then we don't know whether this is a function or not, because we don't have any clue regarding its convergence. But when it does converge, then it can be this power series can be considered as a function of x. To discuss the convergence of power series, we need the notion of radius of convergence. But first, let us prove the following theorem. So that is, if the power series, let's say an x to the power of n, the sum converges at x equal to u, which is non-zero, then it converges. It means this power series converges absolutely at all x such that its absolute value is less than the absolute value of u. Note that x is a variable, so it doesn't have any value yet. So if we specify some specific value, u, such as 1 or 2 or whatever value, some concrete real number, which is non-zero, and if it converges, then we can say that for all x whose absolute value is less than the absolute value of u, this series converges. So that's what this theorem says. So let's try to prove it. So here's proof. Okay, by assumption, since this series a n u to the power of n, so u is some concrete real number. So by assumption, this converges. Converges. So that means this sequence a n times u to the power of n. So this is a real number for each n, right? So this sequence converges to 0. According to a theorem we have already proved somewhere. So that means in particular, this sequence is bounded. So there is an upper bound and lower bound, and that means there exists some real number, let's say m, such that the absolute value of n an times un is less than m for all n. That is greater than or equal to 0. That is what we mean by this sequence is bounded. Now, for any x real number, let us define r equal to x over u, absolute value of it. Then we have the following inequality. That is, so each term in the power series is bounded. So this is equal to a nu to the power of n times x to the power of n over u to the power of n. So this is, since this is bounded here, this is less than or equal to n, and this is r to the power of n. Now, so each term of the power series is bounded above by this quantity. Okay, so if the absolute value of x is less than the absolute value of u, then r is less than 1. So that means this power series absolute value here is less than or equal to this power series, this series actually, m times r to the power of n. R is some constant less than 1. So this has a sum that is m over 1 over r. So this is not infinity. So that means we have a dominating series here of this series. So that it follows that, therefore, this power series an converges absolutely, and we're done. Now, based on this theorem, we can define the radius of convergence. Here's the definition. The radius of convergence of a power series. So given this power series, we first define the set of u, absolute value of u, such that this series converges. A n times u to the power of n converges. So if this converges, then that absolute value of that u is a member of this set, and we take the supremum of this set. So that is the lowest upper bound of this set. So roughly speaking, that is the maximum value of such u. Okay, and that is the radius of convergence of this power series. And obviously, this power series converges if x is equal to 0. Then the power series is just 0 to the power of n is just a 0. So this converges. Therefore, this r, the radius of convergence, must be greater than or equal to 0. So that's the minimum possible value. And depending on the power series, this radius can be finite, positive finite, or infinite. Let us list up all the possible cases, scenarios here. Okay, so when the radius of convergence is greater than 0 and less than infinity, so that means it's finite, then what happens is this. If the absolute value of x is less than r, then the power series converges. And if the absolute value of x is greater than r, then this diverges. By the way, if the absolute value of x is exactly equal to r, we don't know what happens in general. So it depends. It may converge, it may diverge. We don't know. And the second case, when the radius of convergence is infinity, then the power series converges for all real numbers. Converges for all x in reals. And the last case, that is when the radius is 0, then this power series diverges. At all x in real except when x is equal to 0. So we now know what the radius of convergence means, but in practice, how can we calculate the radius of convergence given a power series? For that, we can use Cauchy's criterion or D'Alembert's criterion, which were already explained in another video. So suppose we have a power series, an x to the power of n, with radius of convergence r, okay, radius of convergence. Then first, if this limit exists, limit of nth root of the absolute value of this coefficient an, then the radius of convergence r is given by 1 over L. And 2, if this limit, that is an plus 1 over an, if this limit exists, then the radius of convergence is given by 1 over L. So as you can see, this is derived from Cauchy's criterion. And this comes from D'Alembert's. Excuse me. Lambert's criterion. And here, when L is actually positive infinity, so this can happen, then it is understood as 1 over infinity is equal to 0. Okay? And also, if this limit is 0, then 1 over 0 is understood as positive infinity. Okay? So these are just formal definitions. But what we are really doing is we are taking the 1 over this limit, okay, either this or this, something this, and this may be infinity or 0 depending on this limit. Okay, we don't prove this here, but leave it as an exercise. Now let's see a few examples. First, consider this famous power series, x to the power of n divided by n factorial. So let's try to find the radius of convergence of the series. Here obviously the sequence of the coefficients is 1 over n factorial. So let's calculate this limit. So an plus 1 over an. So that is limit n plus 1 factorial over n factorial, and that is infinity, and 1 over n plus 1, and that is, the limit is 0. Therefore, the radius of convergence is infinity, so that's 1 over 0, and that is infinity. So that means this power series converges for all real numbers. Okay, so x can be any real numbers. And the next example, consider this. X to the power of 2n. So the exponent is even number and odd exponents are absent. So what this means is this. When n is equal to 0, that's 1. When n is equal to 1, then that's x squared. When n is equal to 2, then that's x to the power of 4, and so on. Okay, so if we insist, then we can write this like this. 0 times x plus 1 times x squared, 0 times x cubed plus 1 times x fourth, and so on. So the coefficients of the odd exponent terms are all 0, and the coefficients for even exponent terms are all 1. Okay, so that means we could write a0 is 1, and a1 is 0, and a2 is 1, and a3 is 0, and so on, right? So just 1 and 0 are alternating, one after the other. So obviously this limit, nth power of an, this does not exist. So it's either 0 or 1, so this does not exist. And what about an plus 1 over an? This cannot be defined because the coefficient can be 0, so we cannot divide by 0. So it cannot be defined. Therefore, there's no radius of convergence. So we cannot find it. However, that we cannot find by these methods does not imply that the radius of convergence does not exist. Actually, it does exist. And if we use something called limit sparia, then the radius of convergence can be given as this. Limit sparia, n goes to infinity, nth power of an. So the radius of convergence is given by this. I will explain what this means in another video. But if we just accept this definition, then actually for this power series, this limit superior is actually 1. So the radius of convergence is given as 1 for this power series. So as long as x is, the absolute value of x is less than 1, then this power series converges.